So lesson 5 deals with Euler's method. Again, this is the same Leonard Euler that you've heard of before, dealing with sequences and series and many other things. But it's a method for coming up with a numerical approximation to a solution to a differential equation. If you read along with me here, as we've already seen, many functions have no indefinite integral. For such cases, we need to use numerical methods to approximate those to any desired accuracy. Euler's method is a numerical approach we can use to approximate a solution to a first-order differential equation. So to begin the process, we solve the differential equation for dy over dx in much the same way we did with the direction fields in the last lesson. And we'll just call that f of xy, capital F of xy, because it will end up being some function of x and y that represents our slope. And then remember that dy over dx really just represents the slope. Euler's method makes use of the slope then to predict where the graph will be if we make a small change to the x value. To get a visual for what's going on with Euler's method, I'll go ahead and look at example 1, but I'll go over to Desmos because I've set up something to kind of help you visualize this, kind of animate the process a little bit, kind of like we did with Newton's method back in Calc 1. So given that the solution to the differential equation dy over dx equals negative y passes through the point 0, 1, it wants us to use Euler's method to estimate where the solution will be when x is 0.05 and 0.1. So let me just kind of give you a visual here. Back in Desmos. So I can set this step size in this case. Let me make the step size, well, I'll start with just 0.5 on the screen. So our function f of xy is negative y. So that gives me the slope of our graph anywhere. Just like we had the slope field before, the direction field, that would generate that. It says given that the initial point is 0, 1, so that would be my x naught, y naught. Those coordinates are at 0, 1, so you can see it plotted that point out here. Then if I take this point, it's actually in the slope field. You can see it having the different slopes depending on where it is in the field. And if I take that to this point right here, I'll try to get it centered right over the top of it. It's a little below it. Let's go up just a notch. All right, that's pretty well centered. So at that point, from the slope field, if I would draw a little line segment there like we did with the slope field before, I know that it's sloping down at an angle of negative 1 because it's negative y. And so there's the slope. What Euler's method does is it says, I'm going to just take a step in that direction, a small step in that direction. I've set my step size at 0.5 right here. And so if I take a step in the direction, and the step size is the change in x, by the way. So if I take a step in this direction until I hit an x value of 0.5, it's going to take me right down to this point at 0.5, 0.5. So let me go down here to points and segments just to kind of see how Euler's method's working. So there's the first segment. There's my first step. It'll take me down there, which brings me to this point at 0.5, 0.5. Well, then if I take this movable point and put it right over the top there, you can see the slope is now a little less than that. In fact, since it's at 0.5, 0.5, my slope is just negative y, so my slope's actually negative 0.5 or negative 1/2 there. So if I go over another step of 0.5 in the x direction, then that'll take me over here to where x equals 1 in that direction. So I take a step in the direction of the slope, it takes me over to here, which brings me to this point. If I would continue the process then, I would just say, okay, so what about at this point? Now I can know what the slope is at this particular point. And so it's going to shoot another step out in the direction of the slope at that point. And so that would be an estimate for where the solution will be when x is 1.5. And so that's the basic process for Euler's method. That's what's happening to go from one point to the next. So for our problem, it wants a step size of 0.05, so it's even closer. And that's another thing. The smaller the step size, the more accurate your approximation will be. Just like with any tangent line being used to approximate a function around that point, you need smaller changes in x to make it accurate. So with that in mind, let's go ahead and take a look at this one here. It says, given that the solution to the differential equation dy over dx passes through 0, 1, use Euler's method to estimate where the solution will be when x is 0.05 and when x is 0.1. And so my step size here, you can see I'm going from 0 to 0.05 to 1, or to 0.1. So my step size is my delta x, that's also my h, and that's equal to 0.05. My change in x each time is 0.05. It's going up by 0.05 each time. And so I'll just use h for that rather than delta x. Just easier to work with. So let's say this is the point 0.01, my starting point. I know the slope at that point was -1. So I'm just going to go down 1 over 1 in that direction to get to my next point. So I'm taking that step at a slope of -1 to get my next approximation. Well, I know the slope back here at this point was -1. Again, the slope is just negative the y value, so it's -1. So that means the ratio of the change in y over the change in x has to be -1. Well, I already know with a step size of 0.05 that my change in x is going to be 0.05 from one to the next. Since the slope is -1, my y must be a change of -0.05. That would give me a slope of down 0.05 and over 0.05. That gives me -1 for the slope. Which means the new point, or the next point here, is going to be at an x value of 0.05, because it went from 0, right 0.05 to that. My y went from 1 down by 0.05, so that would take me down to 0.95. Just decreasing 1 by that 0.05. So at this point, I know that my slope will be the negative y, so it's -0.95. And so it's going to almost look like a slope of -1, but let me exaggerate how much different the slope's going to be now. It's not going to be that much different than what it was before. But I know that my change in x, again, is 0.05. My change in y, well, the ratio of the change in y, I'll say delta y, over 0.05, I know has to be this slope of -0.95. So that means that my delta y will equal -0.95 multiplied by 0.05. Notice that this is really just the slope times my delta x here. That's really what I've got. The -0.95 was the slope, the delta x was 0.05. That gives me my change in y. And so that will equal -0.95 times 0.05, -0.0475. And so this new point is going to be, well, the x is easy, I just go up by 0.05 again, so it's going to be at 0.1. And the y will be at 0.95 minus 0.0475, your change in y. So 0.95 minus 0.0475 is 0.9025. And so that would be our approximation there. And so that's just an actual specific example applying Euler's method to see where exactly it would be. If I go back over, if you want a visual of this back in Desmos, I'll just go back up here. First, let me get rid of these pieces. I'll put them back in a second. And I only did 2 iterations of it on the page. So instead of 0.5, I'm going to say 0.05 for my h. I still have the same starting point, still the same slope to begin with. Position this right over the top there. You can see, well, alright, so there's my h. The movable point's very small now. I need to zoom in just so we can see what the slope even is here. There you go. And now generate the points. The next one then is just going to be an offshoot in that direction, and it's going over 0.05 now. And that takes me to this point. And then from there, the slope doesn't really change a whole lot. You can see it's going to be a little bit less. It's not going quite down at the same slope. Not as extreme as I showed it in the notes, but that'll take me then to this point at x2, y2. And so that was my next approximation. And if you want to see what those actual coordinates are, there they are. You've got 0.05 and 0.95. That's the same answer we got. And then 0.1 and 0.9025. That was the estimate of our next point. So that would be a visual to illustrate what we had. If I zoom back out to the window we were on before, it'll look something more like this. So you can see it's really, really close to the actual initial condition point there. So now let's generalize what we just got done doing. To come up with a formula so I don't have to think through it every single time, looking at the triangles, looking at the slope. So to talk about it in general, let's move just from y sub xn, yn over to xn plus 1, yn plus 1. And what's the general formula to do that? Well, the x is easy. Your x sub n plus 1 will just be your previous x value, and then you'll add to it your step size, your delta x. So that's how to generate the next x value. It's always just moving up by the step size. Here it went from 0 to 0.05 to another 0.05, which takes you to 0.1. Just keep going up by that fixed amount each time. So that's the first part. To get the y, I'm going to make use of the fact I know that the change in y over the change in x is approximately, it's my slope, and the slope I'm using is equal to f at the previous value. So xn, yn. This gives me the slope of the function, or of the differential equation, or the slope of the potential solution to the differential equation at xn, yn. And so instead of delta x, I'll call that h. That means that your delta y is equal to h times f of xn, yn. So y is going to go up or down by whatever this number is. So my new y value will be the old y value, and then I'm going to add to that this, my change in y. All right, this is your xn plus your delta x. This is your yn plus your delta y, and that's going to be h times f of xn, yn. So that's what generates the coordinates of the next point in your approximate solution. And you see on the next page, as we can see from the exercise on the previous page, the general formula for y sub n plus 1 using Euler's method is given by this recursive definition. Your n plus first y value is just your nth y value plus h times your function, your derivative at your previous coordinates, your previous point. So we can use that then to fill in this table. And again, the new xn's, I didn't even include the formula right there because it's just the old. I'll go ahead and write it up here. The x sub n plus 1 is just the old x sub n plus h, not a lot to that. So I can fill in that real quick. Example 2 says, use Euler's method with a step size of 0.1 to approximate the solution to this differential equation, where y of 1 is 2.3, and we're on the interval from 1 to 1.5. So my n values are 0 for my initial there, and then 1, 2, 3, 4, and 5, because it's going to take 5 iterations with the step size of 0.1 to get from 1 to 1.5. So my individual x value, since the step size is 0.1, my x1 is going to be 1.1, then it'll be 1.2. I just keep going up by 0.1 each time. And then to get the y values, I'm going to have to use this recursive formula up here. And then we'll deal with the last two here in a little bit. So I'll do the y's in, I'll just keep it blue, I guess. So I know that my y1 will equal my y0 plus my step size, which is h times f at x0, y0. Fill in what these values are. y0 is my first y value, that's 2.3. Plus my step size, that's 0.1. times the function at the previous point. At the previous point, the coordinates were 1 and 2.3. And so the function would be negative 1 times 2.3, which is just negative 2.3. And that gives you your next y coordinate. I'll just put it right down here. So 2.3 plus 0.1 times negative 2.3 is going to give you 2.07. And so that's the next x value, 2.07. To get at the y2, you just repeat the process. It's going to be y1, which was 2.07, plus h, which is still 0.1, times the slope at that previous point. Previous point had coordinates 1.1 and 2.07. And so its slope would be negative x times y. That's negative 1.1 times 2.07. Negative 1.1 times 2.07 is negative 2.277. And so this gives you your next approximation. And that is 1.8423. And then just continuing this process, you can generate the remaining values here pretty quickly. So your y3, continuing this process, will equal the old y value. I'll just say y2 plus 0.1 times negative x2, which was 1.2, times the old y value, which I'll say y2 because that number is going to keep getting bigger and bigger. And that then turns out to be 1.621224. 1.621224. And same process here. Your y4 will be your y3 plus 0.1 times your x3, which is negative 1.3, times your y3 again. And that will be then 1.41046488. And then y5 is y4 plus 0.1 times negative xy would be negative 1.4, because it would be your x4 there, times your y4, which is all of this. I'm just using answer on my calculator to get that. And so this one is 1.212999,797, as far as my calculator will display. 1.212999,797. Barely fit it. Then it says to find the actual solution. Find the actual solution to the differential equation. Use it to calculate the error in each of the approximations. And again, it's not asking for relative error, just asking for actual error here. So if I go back to the original differential equation, dy over dx was equal to negative xy. I can separate and integrate this. This gives me 1 over y dy is equal to negative x dx. So I've separated it. Now integrate. On the left-hand side, that gives me the natural log of the absolute value of y. And on the right, it's negative 1/2 x squared plus a constant. Raising e to both sides, I can see that my y is going to equal, my absolute value of y will equal all of this. And this is really just the same thing as some constant times e to the negative 1/2 x squared, because it's e raised to this times e raised to this. And again, if the absolute value of y is a constant times e to the negative 1/2 x squared, then y is a constant times e to the negative 1/2 x squared. Now, in this particular case, I know it passes through the point 1 and 2.3. When x is 1, y is 2.3. So 2.3 is equal to c times e to the negative 1/2. So that means that my constant c is equal to 2.3 divided by e to the negative 1/2. That's the same thing as multiplying by e to the 1/2. And so my function then, for the actual particular solution here, is c, that's 2.3 e to the 1/2 times e to the minus 1/2 x squared. I could combine these nicer and say this is 2.3 times e to the 1/2 minus 1/2 x squared, or I could say just 1 minus x squared over 2. That would be the particular solution here. Then I can plug these values into the calculator and see what I get. So like when I plug in 1, it should be exactly 2.3. So I can kind of double check what I've entered, make sure it looks right. Trying to make some space here. Document camera kind of in the way, and this makes it dark. I'll move it over here. All right. So 2.3, well first let me do 1, enter, and then 2.3 times e raised to the 1 minus x squared would be answer squared divided by 2, and that'll close the exponent part there. So you can see if you look at the parentheses, you've got the first one, that's this parenthesis right here is just for the exponent on e, and the second one is to get the numerator separate from the denominator. That closes the numerator, and then divided by 2, and then that closes your exponent. Enter. So 2.3. It is correct when I plug in 1, it's at 2.3. So I'll go ahead and fill this value in right here. It's 2.3. When I plug in 1.1 for my x, go back up, it's 2.070746. And I'll just leave it at that. Well, why not? 070746402. I'm going to have to write smaller on the future ones here. And when I plug in 1.2, I get this value, 1.84579323. I'll write a little bit smaller here. 1.84579323. When I plug in 1.3, I get that. 1.6289068813. And then I'll do it again for the next couple here. I'll pause on this end so you don't have to watch me calculate all these. I'll calculate all these and then do the subtractions to get the errors. Let me actually go back here. You can see the error on the first one is 0. On the second one, just look at the difference here. Well, that one's pretty quick. I can see it's 0.000746 something. And then here it's going to be, well, 0.00 something, and then just subtract. You'll have a, what, 1, 5, 6, so on and so forth. And I'll go ahead and fill in the rest of the table and then bring it back up. Okay, so I filled in the rest of those, had a little hiccup right here, but you can see that as I get further and further from the point I know, the error grows and grows and grows. It's still not too bad by the time I get all the way over here, because my step size was so small. I'm only off by 0.01 by the time I get to the last value there. And then I rounded the errors a little bit. Just I'm mainly wanting to see I'm wanting you to see that it's actually growing as I move along. All right. And then down below, the historical note, we've already talked about Leonhard Euler. You probably know all this stuff from the videos that we've had before, but the historical note down here is that Leonhard Euler discovered the constant E for the natural base. He also contributed many of the other notations we use, like I for the imaginary unit, sigma for summations, function notation. Also discovered that e to the ix is cosine of x plus I sine of x, which you proved in the last exam. And so you can ignore this bonus problem. You've actually already done this on the previous exam as part of your exam. And so that does it then for lesson 5.